The universe is drawing its own map. It has been charting the cosmos since the very first moment of the Big Bang, and we are finally learning how to read it. This journey will reveal the hidden blueprint for everything, from the smallest galaxy to the ultimate fate of all existence. We will trace how invisible dark matter scaffolds reality, and how the echo of creation itself guides the growth of the largest structures in the cosmos. By the end, you will see the night sky not as random stars, but as a single, unfolding masterpiece. How did the chaotic birth of everything lead to such intricate order? What invisible hand holds the pen? What does the cosmos see when it looks at itself? That initial map was drawn in a firestorm of pure energy. In the first trillionth of a second, the universe underwent a growth spurt so violent it defies all intuition. A concept known as cosmic inflation took hold, stretching the fabric of space itself faster than light could ever hope to travel. This was not an expansion through space, but an expansion of space, a fundamental swelling of reality. And in that frantic moment, something crucial happened. The quantum world, which is normally a frothing sea of tiny, temporary fluctuations, was caught in the act. Those minuscule ripples in the underlying energy field were stretched and frozen, imprinted across the now vast cosmos as faint variations in density. Think of it like a balloon being inflated so rapidly that the microscopic imperfections on its rubber surface are blown up into a continent-spanning landscape of hills and valleys. These hills and valleys were the universe's first cartographic marks. They were the gravitational seeds, as theorized by physicists like Alan Guth, the subtle pockets of slightly higher density where matter would, over billions of years, begin to gather. We can still see the afterglow of this process today, etched into the cosmic microwave background radiation like a fossilized fingerprint. This relic light shows us the exact pattern of those primordial density variations, the original blueprint from which every galaxy, every cluster, and every vast cosmic web would one day be built. But a blueprint is just a plan. How did this potential, this map of mere possibility, become the solid, structured universe we inhabit? The transformation required an architect, a mysterious and invisible force that could take this faint imprint and begin to build upon it. That invisible framework is the silent partner in the cosmic dance, a ghostly presence whose gravity alone commands the shape of everything. Dark matter acts as the universe's gravitational anchor, a form of substance that does not emit, absorb, or reflect any light, yet possesses immense mass. Its presence is felt, not seen, a cosmic puppeteer pulling the strings of structure from the shadows. Without it, the gentle hills and valleys imprinted by inflation would never have grown deep enough to capture the ordinary matter that makes up our world. The luminous stars and galaxies we admire are merely the decorative lights strung upon this hidden scaffolding. We can visualize this through immense computer simulations, vast digital universes that model how dark matter behaves over billions of years. These simulations reveal dark matter collapsing first into an intricate cosmic web, a sprawling architecture of dense knots connected by long, thin filaments, with enormous empty voids stretching between them. This web is the true skeleton of the cosmos. Ordinary matter, the atoms that form every planet and person, was simply along for the ride. After the universe cooled, this normal matter, which interacts with light, was drawn inexorably into the gravitational wells carved by the dark matter. It flowed into these pre-established basins, pooling and condensing to ignite the first stars and assemble the first galaxies. The pioneering work of astronomers like Vera Rubin provided undeniable evidence for this hidden mass. She found that stars at the outer edges of galaxies orbit just as fast as those near the center, a motion that defied the laws of gravity unless the galaxies were enveloped in massive, invisible halos of dark matter. This unseen substance provided the extra gravitational glue to hold everything together. So the grand map of galaxy clusters and the sprawling cosmic voids is not a map of light, but a map of this dark gravitational landscape. But how do we begin to read this map written in invisible ink? The answer arrives with a cosmic dawn, the moment the first stars switched on and began to trace the dark matter's design with brilliant, luminous fire. That first light was a revolution. After hundreds of millions of years of profound darkness, the universe finally began to switch on. The first stars were not like our sun. They were behemoths, hundreds of times more massive, burning ferociously and dying young in colossal supernova explosions. Their birth was the pivotal moment that ended the cosmic dark ages, but their true legacy was in the radiation they unleashed. This was the dawn of the Epoch of Reionization, a name that sounds complex but describes a beautifully simple, violent process. The intense ultraviolet light from these first stars and early galaxies acted like a cosmic blowtorch, slamming into the vast, cold fog of neutral hydrogen gas that filled all of space. This radiation was so powerful it ripped electrons away from their atomic nuclei, transforming the neutral gas into a hot, diffuse plasma of charged particles. This did more than just light up the cosmos, it fundamentally changed its very nature. The universe became transparent. For the first time, light could travel vast distances without being scattered and absorbed by that primordial hydrogen fog. The universe was creating the very conditions necessary for us to see it. This was the moment the cosmos began to draw its own luminous landmarks. The distribution of these first stars and galaxies was not random. They ignited precisely where the underlying dark matter scaffolding was densest, tracing out the peaks of that hidden gravitational landscape. Their fierce radiation created vast, expanding bubbles of ionized gas, like clearing pockets of mist in a giant forest. These bubbles grew and merged, their edges etching the first coherent, visible structures onto the cosmic canvas. We are now witnessing this ancient cartography with tools like the James Webb Space Telescope. It peers back to this foundational era, not to see the individual stars, but to detect the collective glow of these first galactic communities, seeing how their light is stretched and distorted by the expanding universe. The legacy of this reionization is also encoded in the light from even more distant objects, quasars. As their brilliant beams travel through the now clear universe to reach us, they pass through the last remnants of that neutral hydrogen fog, and their spectra carry specific absorption signatures, a final fingerprint of that great clearing. This epoch set the stage for everything to come. With the universe now transparent and structured, the stage was set for gravity to begin its next, even more ambitious project: the construction of immense cities of galaxies. Gravity's grand construction project culminates in these immense gatherings, the great metropolises of the cosmos. Galaxy clusters are the universe's ultimate cities, each one a dense island of hundreds or even thousands of galaxies, all bound together in a single, swirling gravitational embrace. They do not form just anywhere. These colossal hubs arise only at the most critical intersections of the dark matter web, where the invisible filaments of the cosmic skeleton cross and knot together. Here, the gravitational pull is so overwhelmingly strong that it draws in galaxies from millions of light-years away, pulling them into a bustling, chaotic, and magnificent urban center of stars. Within these clusters, galaxies move at staggering speeds, held fast by the immense, unseen halo of dark matter that makes up most of the cluster's weight. The space between these galaxies is not empty, but filled with a superheated plasma, a ghostly atmosphere so hot it glows in X-rays, revealing the fierce gravitational pressures at play. But the map does not end with these cities. They are themselves organized into something even larger. Superclusters are the continents of the cosmos, immense chains and sheets of galaxy clusters that can stretch for 500 million light-years or more. Our own home, the Milky Way, resides within one such structure, the Laniakea supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for a gravitational domain so vast it contains over 100,000 galaxies. We are not at its center, but rather on a suburban outskirts, part of a great cosmic flow where entire galaxy clusters stream along invisible riverbeds of dark matter toward a central gravitational basin known as the Great Attractor. This motion is not random drift. It is the universe continuing to draw its map in real time, a slow, stately dance choreographed over billions of years. By observing the distribution and movement of these great metropolises, astronomers can trace the underlying topography of the cosmos, weighing the unseen mass that dictates the paths of everything we see. Yet even this continent-spanning structure is just a single feature in a pattern of breathtaking scale. To see the universe's true self-portrait, we must pull back to witness the entire canvas. From this grand, continental scale, the final pattern emerges. The cosmic web is the universe's ultimate cartographic masterpiece, the finished canvas after 13.8 billion years of work. If you could step outside of space and time to look upon the entirety of the cosmos, you would not see a random scattering of lights. Instead, you would witness a single, colossal architecture, a luminous sponge woven from threads of galaxies. This is the largest pattern in all of existence, a three-dimensional tapestry of dense clusters, long, delicate filaments, vast, curving sheets, and immense, dark voids that stretch for hundreds of millions of light years. This is not a static picture. It is a living structure, the final evolved state of those faint gravitational seeds planted during the universe's first frantic moments. The filaments themselves act as cosmic superhighways, rivers of dark matter and intergalactic gas that channel material toward the bustling hubs of galaxy clusters. This relentless flow of matter, guided by gravity, makes the dense knots of the web grow ever denser over eons, and the voids, which make up most of the universe's volume, are not completely barren. They are the cosmic countryside, regions of exceptionally low density where matter is so scarce that a single, lonely galaxy might feel like a solitary farmhouse on an endless, dark prairie. This magnificent web is a triumphant confirmation of our most successful model of the universe, known as the Lambda-CDM model. It predicts that dark matter and dark energy should sculpt the cosmos into exactly this kind of vast, web-like structure. And we have seen it with our own eyes. Massive astronomical surveys, like the Sloan Digital Sky Survey, have meticulously mapped the positions of millions of galaxies. When we plot their locations in 3 dimensions, the cosmic web appears before us, a statistical ghost made real by countless points of data. This is the signature of the universe's self-organizing principles, a pattern written by the simple, relentless law of gravity acting on a dark and invisible foundation. But such a perfect map requires perfect tools to draw its lines. The universe used the most fundamental messengers imaginable, particles that have been tracing its contours since the first second of time. This ancient light is the universe's baby picture. The cosmic microwave background radiation is a faint, cold glow that fills every corner of the sky, a direct relic from a time when the cosmos was a mere 380,000 years old. Before this moment, the universe was an opaque, searing plasma, so dense that light was trapped, constantly bouncing between particles. Then, as the universe expanded and cooled, electrons and protons combined to form the first neutral atoms. In that instant, space became transparent, and that trapped light was suddenly set free, streaming across the cosmos. We are still bathing in that afterglow today, a fossilized echo of creation itself. But this glow is not perfectly smooth. If you look closely, it is a speckled canvas of incredibly subtle hot and cold spots, tiny temperature variations known as anisotropies. This pattern is not random noise. It is a literal snapshot of the universe's gravitational blueprint at that precise moment in its infancy. Each slightly warmer patch marks a region that was a little denser, a gravitational well in the making. Each cooler spot is a region that was slightly more empty, a future cosmic void. These are the exact same density variations imprinted by cosmic inflation, now frozen into this first light. They are the gravitational seeds for everything that would follow, from the smallest dwarf galaxy to the largest supercluster. Space telescopes like Planck have spent years mapping this subtle speckling with breathtaking precision. They have produced the most detailed map we have of the infant universe, a cartographic record of its initial conditions. By analyzing the statistical properties of these hot and cold spots, their sizes and their distribution, cosmologists can measure the fundamental ingredients of the cosmos. This map tells us the exact proportions of ordinary matter, and dark energy. It confirms the universe is geometrically flat, and it provides our strongest evidence for that initial, violent period of inflation. The cosmic microwave background is the ultimate Rosetta Stone, allowing us to decode the universe's birth certificate. It draws a direct, unbroken line from the quantum ripples of the first instant to the grand cosmic web we see today. But a map, even one this profound, is only a record of a moment in time. It shows us the starting point, but the journey itself is governed by a deeper set of rules, the fundamental laws that dictate how this cosmic cartography unfolds across the eons. These fundamental laws are the cartographer's unbreakable rules. Every line drawn across the cosmos, from the spiral arm of a galaxy to the curve of a gravitational well, follows a strict code written into the fabric of reality. This code is defined by the fundamental constants and forces, a set of numerical values and physical laws so precise that they seem almost tailor-made for building a complex universe. The gravitational constant, for example, is the universe's master architect, dictating the strength of the gravitational pull between any two objects. If this number were even a fraction weaker, matter would never have clumped together. The cosmic gas would have simply drifted apart forever into an eternal, featureless haze. If it were slightly stronger, the universe would have collapsed back on itself in a catastrophic big crunch long before stars could ever form. This delicate balance is the cartographer's first and most important rule. It governs the pace of cosmic construction, deciding how quickly a cloud of hydrogen can collapse to ignite a star, or how powerfully a galaxy cluster can pull in its members. Alongside gravity, the nuclear forces act as the cosmic sculptors. The strong nuclear force binds protons and neutrons together in atomic nuclei, forging the heavy elements that are the building blocks of planets and life. Without its precise strength, the furnaces of stars would be cold and inert, unable to create anything more complex than hydrogen. The weak nuclear force guides the process of radioactive decay, a crucial step in how stars transmute elements. And electromagnetism, the force that holds atoms and molecules together, provides the structural integrity for all tangible matter. These forces work in concert, guided by the laws of thermodynamics which control the flow and transformation of energy, and by quantum mechanics, which provided the initial random flicker of density variations that started it all. The master framework that ties everything together is Einstein's theory of general relativity. This is the theory that describes gravity not as a simple force, but as the curvature of spacetime itself by mass and energy. It is the theory that gives us the cartographer's canvas, a dynamic, flexible fabric that can be warped and woven. Every galaxy, every star, every planet creates a dent in this spacetime fabric, and it is the shape of these dents that guides the motion of everything else. This is the gravitational landscape that dark matter and galaxies traverse. The unwavering consistency of these laws is what makes the cosmic map possible. The strength of gravity is the same in a distant quasar as it is in our own solar system. The speed of light is a universal speed limit that never changes. This reliability means the universe is not a chaotic, lawless place, but a system that follows a predictable, mathematical pathway. The same simple rules applied everywhere and to everything allowed the faint quantum seeds from the Big Bang to evolve, step by mathematical step, into the magnificent cosmic web we see today. The tools were perfect and the instructions were clear, but with the map now drawn, a new question emerges. What is the ultimate purpose of this grand design, and what will become of it in the distant future? This grand cosmic map is constantly being edited and revised. The universe is not a static portrait but a dynamic, living document, and its most powerful editing tools are the explosive cycles of creation and destruction. Take the life of a single, massive star. It burns brilliantly for millions of years, but its death is where its true cartographic influence begins. When it explodes as a supernova, it does more than just light up the sky. It scatters a rich dust of heavy elements forged in its core. Carbon, oxygen, iron, the very stuff of planets and life, across vast stretches of space. This stellar debris enriches the cosmic gas clouds, but the explosion itself is a double-edged sword. The immense shockwave can slam into nearby gas clouds, compressing them so violently that it triggers the collapse and birth of a new generation of stars. Yet that same cataclysm can also blast other gas clouds apart, stripping them of the material they need to form stars at all. This is stellar feedback, a local but powerful mechanism where a star's death directly dictates where new stars can and cannot be born, redrawing the local galactic map. On a far grander scale, an even more powerful editor resides at the heart of most galaxies. Supermassive black holes with gravitational pulls so strong that not even light can escape are paradoxically some of the universe's most brilliant artists. As vast amounts of gas and dust spiral into these cosmic voids, the material heats to incredible temperatures, glowing intensely and sometimes powering colossal jets of energy that scream across space. This outpouring of energy acts like a cosmic thermostat. When a galaxy grows too massive and its central black hole feasts on too much material, the resulting outburst heats the surrounding galactic gas, preventing it from cooling down and collapsing to form new stars. This feedback process puts a brake on runaway galaxy growth, ensuring no single structure becomes too dominant. It is a self-correcting mechanism written into the laws of physics, a way for the universe to maintain balance in its grand ecosystem. Without it, galaxies would greedily consume all available fuel, resulting in a monotonous cosmos of overgrown, star-packed behemoths. This dynamic tension is what creates the rich, varied tapestry we see. Gravity is the relentless force that pulls matter together, building structure and drawing the map's lines. Feedback is the countervailing force, the cosmic pressure that pushes back, erasing some details while accentuating others. It is this eternal interplay that carves out the delicate filaments of the cosmic web and maintains the vast, empty stretches of the voids. The universe is not simply unfolding according to an initial blueprint. It is actively refining its own design through these complex, energetic conversations. For a spectacular demonstration of this dynamic mapping, we need only observe the most violent collisions in the cosmos, where entire galaxies meet. These brilliant beacons shine from the very edge of space and time, offering a unique form of cosmic illumination. Quasars are the most powerful and sustained energy sources in the universe, each one a supermassive black hole at the heart of a distant galaxy, feasting on an enormous disk of gas and dust. As this material spirals into the abyss, it heats to millions of degrees, unleashing a torrent of radiation that can outshine every star in its home galaxy combined. For us, they act as lighthouses, their piercing beams cutting across billions of light-years of near emptiness. Their true cartographic power, however, lies not just in their raw brilliance, but in what happens to their light on its long journey to our telescopes. As a quasar's light travels toward Earth, it passes through the sparse, wispy filaments of the cosmic web, the vast rivers of gas that flow between galaxies. This gas is mostly hydrogen, and it leaves a distinct fingerprint on the light. Hydrogen atoms are tuned to absorb a very specific color of ultraviolet light. So when the quasar's beam, containing every color of the rainbow, passes through a cloud of this intergalactic hydrogen, that particular color is plucked right out of the spectrum. Because the universe is expanding, light from more distant gas clouds is stretched more, shifting the absorption to different, redder wavelengths. The result is a stunningly detailed barcode. A single quasar's spectrum reveals not one, but thousands of these dark absorption lines, each one corresponding to a different cloud of hydrogen at a different distance along the line of sight. Astronomers call this the Lyman alpha forest. This forest of lines is a direct core sample of the cosmic web, a one-dimensional map of all the diffuse matter lying between that distant quasar and us. By pointing our telescopes at many different quasars in many different directions, we can stitch these one-dimensional probes together. Each quasar gives us a core sample, like a straw pushed through a complex layer cake. With enough straws in enough places, we can begin to reconstruct the full three-dimensional architecture of the invisible filaments and voids. Quasars are not just tools, they are also signposts. They tend to reside in the most densely packed neighborhoods of the early universe, the nascent hubs that would one day grow into immense galaxy clusters. Their very existence marks a region of extreme gravitational activity on the cosmic map, and the incredible energy they release acts as a powerful feedback mechanism, regulating the growth of their host galaxies and helping to sculpt the final form of the cosmic web. These distant lighthouses guide us through the darkest voids, but to complete our cartographic mission, we must assemble every piece of evidence into one unified view of reality. To test these grand theories, we build entire universes from scratch. Inside the world's most powerful supercomputers, cosmologists run vast digital experiments known as hydrodynamic simulations. Projects like Illustris, TNG, and Eagle begin with a virtual box of space, filled with billions of particles representing dark matter and ordinary gas. They program in all the known rules, the fundamental laws of gravity, the physics of how gases cool and collapse, and the complex feedback from exploding stars and ravenous black holes. Then they set the simulation in motion, starting from conditions just after the Big Bang and pressing play. Over months of computing time, these simulations fast-forward through 13.8 billion years of cosmic history. We get to watch it happen. From a nearly smooth, expanding cloud, a familiar architecture slowly emerges. The dark matter particles, guided only by gravity, first collapse into a delicate, web-like scaffold. Then, the ordinary gas flows along this invisible skeleton, pooling at the intersections to ignite virtual galaxies. These digital galaxies evolve, collide, and even develop spiral arms and central black holes, all without any direct human input. The final result is a synthetic sky, a complete cosmic map generated by the unyielding logic of physics. The true power emerges when we compare this digital universe to our own. We can place a virtual telescope inside the simulation and create an image that mimics what our real telescopes like Hubble or James Webb would see. When the two maps align, when the distribution of galaxies, the properties of clusters, and the structure of the cosmic web look the same, it is a profound validation. It tells us our understanding of the core physics is likely correct, but the real breakthroughs often come from the mismatches. If the simulated universe produces too many small satellite galaxies, or if its galaxies are too massive, it points directly to a flaw in our models. Perhaps our understanding of supernova feedback is incomplete, or the nature of dark matter is different than we assumed. We can then adjust the rules in the simulation, running it again and again, until the digital cosmos better reflects reality. This process transforms cosmology from a passive science of observation into an active science of experimentation. These synthetic universes reveal something even more profound. The emergence of the cosmic web is not a random accident, but a direct and almost inevitable outcome. Given the initial conditions from the cosmic microwave background and the standard laws of physics, the complex tapestry of clusters, filaments, and voids seems destined to form. The universe's self-mapping is a computational process of staggering scale, a calculation that has been running since the beginning of time. Our most powerful machines are now allowing us to glimpse the underlying algorithm. This principle of look-back time transforms our telescopes into genuine time machines. When you gaze at the faint smudge of the Andromeda galaxy, you are not seeing it as it is tonight, but as it was 2.5 million years ago, its light only just now completing its long journey to your eyes. This is not a philosophical abstraction. It is a direct physical consequence of the finite speed of light. Astronomers exploit this fact to perform the ultimate historical analysis. By systematically observing galaxies at progressively greater distances, we are effectively drilling core samples back through cosmic time, compiling a fossil record of the universe's structural evolution. A galaxy 1 billion light-years away is a snapshot from 1 billion years in the past. We can directly compare that ancient galaxy to a similar one 5 billion light-years away, which is 5 billion years older in its development. This allows us to construct a chronological sequence, a flipbook of cosmic history that shows the map growing and changing. What we see is a universe that becomes more structured with age. In the deep past, the cosmos was a more crowded and chaotic place, filled with a multitude of smaller, irregular blobs of stars, the primordial building blocks known as proto-galaxies. These fledgling structures were more numerous and far more active, blazing with the light of newly formed stars. Over billions of years, the relentless pull of gravity orchestrated a grand consolidation. We can observe these smaller galaxies streaming along the dark matter filaments, drawn toward one another in a slow-motion dance. They collide and merge, their stars mingling to form larger, more stable galaxies like our own Milky Way. This process is called hierarchical structure formation, and it is the dominant story of cosmic growth. Small structures build larger ones. We see the evidence in the halos of large galaxies, which are littered with the remnants of smaller galaxies they have consumed, like cosmic archaeological sites. This four-dimensional cartography, mapping 3 dimensions of space across the 4th dimension of time, reveals a universe that is not static but dynamically assembling itself. The map was simpler, fainter, and more uniform in its youth. Today, it is a complex tapestry of grand designs, a testament to billions of years of gravitational sculpting. Watching this chronological unfold is like viewing a time-lapse of a giant redwood tree growing from a sapling, each frame capturing 1,000,000 years of progress. Our cosmic atlas has a final page, a boundary beyond which we cannot read. This is the horizon of the observable universe, a sphere centered on us with a radius of roughly 46.5 billion light-years. It is crucial to understand this is not a physical wall, not an edge where galaxies simply stop. It is a horizon of information, a limit set by the simple, unbreakable laws of physics. The universe is 13.8 billion years old, and light travels at a finite speed. We can only see the regions of space from which light has had sufficient time to reach us since the dawn of time. Every star, every galaxy you have ever seen or heard of exists inside this sphere. Beyond it, there could be an infinity of other galaxies, other worlds, other cosmic webs, but their light has not yet arrived and may never will. This means our magnificent map of everything is fundamentally and forever incomplete. We are not charting the cosmos, we are only charting our local cosmic neighborhood, a single island in what might be an endless sea. This reality is made even more profound by the accelerating expansion of the universe. Galaxies that are today near the very edge of our observable horizon are being carried away from us by the stretching of space itself at speeds that will eventually surpass the speed of light. From our perspective, they will appear to slow down, their light reddening into oblivion before they vanish entirely from our future sky. They cross over this informational horizon, disappearing from our map not because they have been destroyed, but because their signal can no longer reach us. This defines the ultimate extent of our possible knowledge, a volume sometimes called the Hubble volume. What lies beyond is the realm of pure theory. Cosmologists speculate that our entire observable universe might be just one bubble in a vast, frothing multiverse, a consequence of eternal inflation. In this staggering picture, other bubbles could exist with entirely different fundamental laws, different strengths of gravity, perhaps even different numbers of spatial dimensions. They would have their own cosmic maps, drawn with rules we cannot possibly imagine. Our entire understanding of reality, from the quantum flutter to the grand web, is confined to this single, luminous sphere we can see. It is a humbling reminder that for all our knowledge, we are cartographers of a single continent, unaware of the true scale of the world we inhabit. To peer even slightly deeper into this mystery, we must turn to the next generation of tools, instruments designed to push against the very limits of sight. These new instruments are our species' collective effort to read the universe's handwriting with perfect clarity. The next generation of cosmic cartography is already taking shape in the form of colossal new observatories, each designed to map a different layer of reality. On a mountaintop in Chile, the Vera Sea, Rubin Observatory is preparing for a monumental task. Its legacy survey of space and time will act as the most patient and meticulous sky watcher in history. Over the course of a decade, it will photograph the entire southern sky every few nights, creating a colossal time-lapse movie of the cosmos. It will not simply catalog billions of galaxies, it will watch them, tracking their subtle movements and changes in brightness over years. This dynamic map will reveal how the cosmic web is shifting in real time, charting the gravitational flows that pull entire galaxies through space. Meanwhile, the Nancy Grace Roman Space Telescope will serve as our infrared eye in the heavens. Its wide field view is perfectly suited for peering through veils of cosmic dust that obscure visible light, uncovering hidden galaxies and stellar nurseries. Its most profound work, however, will be mapping the invisible. By observing how the light from distant galaxies is subtly warped and distorted by the gravity of intervening dark matter, a phenomenon called weak gravitational lensing, Roman will create an unprecedented chart of the dark matter web itself. It will show us the hidden skeleton in stunning detail, tracing its distribution across billions of light years. But to understand the origins of this map, we must listen. The Square Kilometre Array, a sprawling network of radio telescopes across 2 continents, will be the most sensitive listening post ever built. It will tune its receivers to the faint radio whisper of neutral hydrogen, the most abundant element in the universe. This hydrogen traces the cosmic web in its rawest form, and because radio waves travel to us from the deepest reaches of space, the SKA will effectively hear this web as it was billions of years ago. It will produce a 3-dimensional map of the universe's structure during its formative years, showing us the filamentary rivers of gas before they fully collapsed into galaxies. These are not solitary efforts. Missions like the European Space Agency's Euclid telescope are already joining this grand campaign, providing complementary data to weigh dark energy and dark matter. The flood of information from these projects will be staggering, a fire hose of data, is so immense it will require new branches of computer science and artificial intelligence just to process. This will not be a simple update to our existing charts. This new, ultra-precise map will confront our most cherished theories with cold, hard evidence. The detailed structure of the cosmic web, the precise rate of its expansion, and the behavior of dark matter on the smallest scales will put our models to the ultimate test. Any tiny deviation, any small anomaly in the data, could be the first crack revealing an entirely new layer of physics. These future cartographers may not just fill in the blank spots on our map. They might discover entirely new continents, or reveal that the paper our map is drawn on is fundamentally different than we ever imagined. The ultimate goal is to decode not just the map, but the mind of the cartographer, to understand the fundamental nature of the forces that have been sketching this grand design since the first moment of time. The mathematical perfection of the cosmic map forces a question that lies beyond the reach of any telescope. Could the universe itself be a form of mind? The laws of physics operate with an unerring, almost artistic precision, weaving chaos into intricate structure according to a deep mathematical logic. This breathtaking order has led some to wonder if a kind of cosmic consciousness is at work, a self-organizing principle woven into the fabric of reality. From ancient philosophers who saw the cosmos as a living being to modern theoretical physicists who entertain the idea of a participatory universe, the notion persists that reality might possess a latent form of awareness. Perhaps the universe is not just a place, but a process, a vast computational system thinking itself into existence. Yet there is a powerful counter-argument, one rooted in the science of complexity and emergence. The appearance of a grand design could be a magnificent illusion. A beehive exhibits stunning architectural order, yet no single bee holds the blueprint. The complex pattern emerges from the simple, blind interactions of countless individuals following basic rules. In the same way, the cosmic web may be the ultimate emergent phenomenon. The fundamental laws are the only cartographer we need, a set of blind, impersonal, and yet astonishingly creative rules. When you run a simple mathematical equation through countless iterations, complex and beautiful patterns inevitably arise. The universe has been running its equations for nearly 14 billion years. The spiral of a galaxy and the branching of a tree may both be expressions of the same underlying mathematical truths, unfolding without any need for a guiding intelligence. This places us at a profound crossroads between science and philosophy. It challenges our very definitions of what mind is and what matter can do. Does a system that processes information and computes its own structure across billions of years possess a form of consciousness, even if it is nothing like our own? Or are we simply witnessing the magnificent, inevitable consequence of a universe built with a specific, and perhaps unique, set of operational parameters? The universe maps itself not with intention, but with the relentless, logical outcome of its own foundational code. The map and the mapper may be one and the same, a self-writing story whose first and only author is reality itself. Our ancestors gazed at the same darkness and saw stories written in starlight. They looked up and did not see random points of light, but epic figures, sacred animals, and divine pathways etched across the night. The constellation of Orion the Hunter, the great serpent Draco, the seven sisters of the Pleiades, these were not just pictures. They were the first layers of a celestial map, a human attempt to project order onto the vast and seemingly chaotic cosmos. This was an act of profound intuition, a recognition that the universe possessed a rhythm, a pattern that could be named and understood. For the ancient Babylonians, this mapping was a precise science of omens. Their Apin clay tablets are among the oldest known astronomical documents, meticulously cataloging the risings and settings of stars and planets. They saw the movements of celestial bodies as direct messages from the gods, a divine script that governed the fates of kings and empires. Their zodiac, a belt of constellations through which the sun, moon, and planets traveled, became a fundamental clockwork for the cosmos, linking human time to celestial cycles. In the Americas, the Maya developed their own incredibly sophisticated cartography of time. Their codices track the cycles of Venus with stunning accuracy, correlating the planet's appearances with events on Earth. Their cosmos was a layered reality with upper, middle, and underworlds, all connected by a great world tree, the Waka Chen, whose roots and branches held the heavens and the earth in a sacred balance. This concept of a central axis, an axis mundi connecting different realms of existence, appears in myths across the globe. From the Norse Yggdrasil to the Siberian world tree, it represents a universal human understanding that reality is structured and interconnected. Perhaps the most profound and intimate form of this ancient mapping is found in the Aboriginal Australian concept of songlines. These are not maps drawn on paper, but sung into existence. The landscape itself, and the stars above it, are part of a single, continuous story of creation. By singing the ancient songs while walking across the desert, an individual navigates the physical world and simultaneously reenacts the journeys of the ancestral beings who formed it. The path and the song are one, a living map where geography, astronomy, and mythology are fused into a single, navigable reality. What all these systems share is a deep, foundational belief that the cosmos is not random. It has an architecture, a moral and spiritual order that human life is intimately woven into. The stars were not distant nuclear furnaces, they were ancestors, guides, and gods. The patterns were not just for navigation, they were a language. Our modern scientific quest to decode dark matter and trace the cosmic web is, in its essence, the very same human urge. We have traded clay tablets for space telescopes and mythological beasts for dark matter halos, but the fundamental question remains unchanged. Where do we fit within this grand design? We are still the ancient cartographers, using the best tools we have to read a map that was drawn long before we ever looked up. Every map we have ever drawn is a simplified version of reality. Our cosmic charts, from the intricate web of dark matter to the elegant equations of general relativity, are not the universe itself. They are models, incredibly powerful and successful ones, but still just approximations of a deeper, more complex truth. Think of a street map of a great city. It shows you the roads and landmarks, but it cannot capture the feeling of the wind between the skyscrapers, the sound of a bustling market, or the hidden life in the sewers and subway tunnels below. Our cosmological models are much the same. They give us the structure, the grand avenues of gravity, and the intersections of galaxy clusters, but they are silent on the full, lived experience of the cosmos. The Lambda CDM model, with its dark matter and dark energy, is our best available street map. It predicts the distribution of galaxies with stunning accuracy and explains the universe's accelerating expansion. Yet, for all its success, it is built upon foundations we do not fundamentally comprehend. Dark matter is a label for a gravitational effect we observe, not an understood substance. Dark energy is a name for a repulsive force whose nature is a complete mystery. We are navigating by these names, trusting the map because it gets us where we need to go, all the while knowing the actual terrain is made of something else entirely. This reliance on observation through light is our greatest limitation. We are cartographers of the visible, mapping a universe we can only see. But what if most of the territory is invisible? Our situation is like that of a sailor on a vast, dark ocean. We can measure the height and frequency of the waves on the surface, we can chart the currents, and we can predict the tides. From this, we can infer the existence of the deep, the immense volume of water beneath us. But we have no idea what lives in that abyss. We do not know its topography, its strange chemistry, or the creatures that might swim in its perpetual night. The true cosmos is that ocean, and our telescopes only skim the luminous surface. The quest for a theory of quantum gravity is the attempt to build a submarine, to dive into those depths and see the universe as it truly is, not just as it appears through the filter of light. Such a theory could render our current map obsolete, revealing that dark matter and dark energy are merely shadows cast by processes occurring on scales a billion times smaller than an atom. The fabric of spacetime itself might be woven from discrete, quantum threads, a pixelated reality where our smooth, continuous maps are nothing but a useful illusion. This is not a failure of science, but its very engine. The imperfections in our models, the tiny discrepancies between prediction and observation, are not errors to be erased. They are the whispers from the deeper territory, the clues that guide us toward the next revolution. Embracing this humility is what allows discovery to flourish. Our maps are not gospel. They are the best stories we can tell with the evidence we have. And the most exciting part of the story is knowing that the next chapter will likely rewrite everything we think we understand. The map of reality might not be what it seems. What if the sprawling three-dimensional cosmos with its galaxies and voids is merely a projection, a cosmic illusion? This is the startling proposition of the holographic principle, a theory that forces us to redraw our charts in the most radical way imaginable. It suggests that all the information needed to describe a volume of space, including every star, every planet, and every one of us, could be perfectly encoded on a two-dimensional surface that surrounds it. Think of a security hologram on a credit card. The flat, shiny surface contains all the data necessary to project a seemingly three-dimensional image that shifts as you move. The holographic principle applies this same logic to the entire universe. Our rich, three-dimensional reality might be a magnificent projection from a vast, distant, two-dimensional screen. The inspiration for this incredible idea comes from the most enigmatic objects in the cosmos, black holes. Physicists studying black hole thermodynamics discovered a profound puzzle. The amount of information a black hole can contain seems to be proportional not to its volume, like a normal storage device, but to the surface area of its event horizon. This was a bizarre clue that the fundamental description of space might reside on its boundary, not within it. If this is true for black holes, could it be true for the universe as a whole? In this view, the ultimate cartographer is not mapping space, but pure information. The cosmic web, with all its intricate filaments and clusters, would be a holographic mirage. The true map of everything is a vast, two-dimensional information field, a kind of cosmic film from which our three-dimensional world is projected. This means the universe's self-cartography operates on a level far more alien and fundamental than we ever conceived. We are not just reading a map of the cosmos, we might be living inside a projection of that map. The solidity of the world around us, the very sense of depth and dimension, could be an emergent property of information processing on a flat surface. This idea is not just philosophical speculation. It is a serious, albeit highly theoretical, attempt to bridge the greatest divide in modern physics, the gap between Einstein's theory of gravity and the quantum mechanics of the very small. It suggests that to find the final, true cartographer, we must stop looking at the stars and start deciphering the code written on the boundary of reality itself. If this principle holds, then our entire understanding of the cosmic map, from the Big Bang to the cosmic web, requires a complete rewrite. The territory and the map would be fundamentally inseparable, two expressions of the same underlying truth. Our cosmic map feels perfectly tailored for our existence. The precise strength of gravity, the exact charge of an electron, the very nature of the nuclear forces, all seem fine-tuned to an almost impossible degree. If any of these numbers were even slightly different, the universe would be a barren wasteland. Stars would not burn, atoms would not bond, and complexity would never arise. This perfect calibration leads to a profound and puzzling question. Why is our universe so hospitable? This is the heart of the anthropic question. and its answer may lie not within our universe, but outside of it. Some of our most advanced theoretical frameworks, like string theory, point toward a staggering possibility. Instead of one universe, there could be a nearly infinite multiverse, a vast landscape of cosmic bubbles. In each of these bubbles, the fundamental constants and even the number of spatial dimensions could be randomly different. In this cosmic lottery, most universes would be stillborn or barren. They might collapse instantly or be nothing but a featureless soup of particles. But in a tiny, tiny fraction of these universes, the numbers would line up by pure chance, creating the precise conditions needed for galaxies to form, for stars to shine, and for life to emerge. In this view, our universe is not special. It is not designed. It is simply the one we happen to live in because, well, we are here to observe it. Our specific cosmic map, with its particular rules for gravity and particle physics, is just one possible page in an infinite cosmic atlas. The cartographer is not a conscious designer, but a blind, automatic process of universe generation. The focus of our inquiry then shifts dramatically. We stop asking why the universe is this way, and start asking how it operates given that it is this way. Our existence acts as a powerful selection effect, a filter that guarantees we will only ever find ourselves in a universe capable of producing us. While this anthropic reasoning is controversial, as it can feel like a tautology, it forces a radical humility upon cosmology. It suggests that the deep laws we are trying to decode might not be fundamental at all. They could be local bylaws, specific to our cosmic neighborhood, with entirely different physics operating just beyond our observational horizon. The search for a single, elegant theory of everything might be misguided if the true nature of reality is an endless, teeming garden of different realities. Our entire observable universe, with its magnificent cosmic web and 13.8 billion years of history, could be just a single, habitable island in an archipelago of unimaginable scale. The universe's grand design is not a permanent monument. It is a temporary masterpiece destined to fade. Our current cosmic epoch, rich with galaxies and structure, is a fleeting golden age in a much longer and darker story. The driving force behind this eventual dissolution is dark energy, the mysterious repulsive energy causing the expansion of space to accelerate. This is not a gentle drift, but a gathering storm that will ultimately tear the cosmic map apart. For now, gravity still holds sway within local groups of galaxies. Our own Milky Way, Andromeda, and a few dozen smaller neighbors are bound together in a gravitational dance that will continue for trillions of years, eventually merging into one large galaxy. This will be an island universe, a single, isolated city of stars in an ever-darkening ocean. But beyond this local group, the fate is far more lonely. As the expansion of space accelerates, the distant galaxies we see today will first redden as their light is stretched to longer and longer wavelengths. Then they will simply vanish. They are not moving away through space, but the space between us is stretching so fast that their light can no longer bridge the growing chasm. One by one, the lights of the cosmic web will wink out, each galaxy cluster becoming an isolated island, forever unaware of the others. The filaments of the web, those great rivers of dark matter and gas, will be stretched and severed. New star formation will grind to a halt as the raw material for new stars is locked away in these isolated galactic islands, or dispersed into a void too vast for gravity to pull it back together. The stars themselves will slowly burn out. The universe, once ablaze with the light of a trillion galaxies, will grow dim. After all the stars have died, their remnants will either be consumed by black holes or drift as cold, dead cinders. This is the path to the heat death, the ultimate state of maximum entropy. In this final chapter, all energy is evenly distributed, all temperature differences have been erased, and no work can ever be done again. The cosmos becomes a uniform, ultra-thin soup of particles, hovering just above absolute zero. It is a state of perfect equilibrium and perfect stillness. The intricate map of clusters and filaments, painstakingly drawn over billions of years by gravity, will have been smoothed away into an absolute and eternal blankness. The cartographic process that began with a quantum whisper will end in a silent, featureless sea. The universe will have completed its cycle from a simple, hot unity to an era of magnificent complexity, and back again to a cold, final unity. The map erases itself. The universe's grand map begins not with certainty but with a ghostly haze of possibilities. At the quantum scale, particles do not have fixed positions, only clouds of probability. An electron is not a tiny planet orbiting a nucleus. It is a shimmer of potential, a set of overlapping chances for where it might be found. This is the quantum fog, the fundamental blur from which all sharp reality must somehow emerge. So how does this fog of maybes coalesce into the definite hills and valleys of the cosmic microwave background, the very seeds of galaxies? The answer lies in a subtle but powerful process known as quantum decoherence. In the universe's first fiery moments, the tiny quantum fluctuations in energy were intimately linked to the fabric of spacetime itself. Each ripple in the quantum field created a minuscule ripple in gravity. As the cosmos expanded at a staggering rate, these linked systems were pulled apart. The quantum possibilities, no longer able to maintain their delicate, overlapping states, began to decohere. They lost their quantum coherence, collapsing from a spectrum of potential outcomes into one specific, classical reality. It was as if the universe, through its own rapid growth and cooling, performed a measurement on itself. The quantum wave, function of the entire cosmos, collapsed, selecting one specific configuration from an infinite menu of possibilities, and in doing so, it printed the specific pattern of hot and cold spots we now see etched across the cosmic microwave background. This was the moment probability crystallized into destiny, giving us the unique cosmic map we now inhabit. This profound link between measurement and reality leads to an even more startling idea. Some interpretations of quantum mechanics suggest that conscious observation is not a passive act, but an integral part of defining what is real. While this view is hotly debated and far from settled science, it proposes a breathtaking symmetry. The universe, through its own physical evolution, creates the conditions for life. That life, in turn, evolves to become conscious and to look back out at the cosmos. In observing the universe, in measuring it and mapping its grand design, we may be completing a cosmic circuit. The map is not merely discovered by an independent observer. It is finalized through the very act of observation. The cartographer and the cosmos become entangled in a participatory loop, a final reflexive step in the universe's long journey to know itself. This grand design sings the same song at every possible volume. The universe's self-mapping is a symphony played across an incredible range of scales, from the quantum whisper to the cosmic shout. The entire architectural process began in a realm of reality so tiny it defies all human intuition. The quantum fluctuations that seeded the cosmic web originated at scales near the Planck length, a distance so minuscule it is a millionth of a billionth of a billionth of a billionth of a meter. At this frontier, the very concepts of space and time break down. Yet, from this chaotic, foaming foundation, the first notes of the symphony were played. Cosmic inflation acted as a universal amplifier, taking those faint quantum vibrations and stretching them to macroscopic proportions, blowing them up into the hills and valleys of density that would one day become everything. Then, gravity took over as the conductor, orchestrating the slow, patient growth of these seeds over billions of years. The result is a composition of breathtaking scope. The same faint ripple that began smaller than a subatomic particle can be linked directly to the largest known structure in the universe. The Hercules Corona Borealis Great Wall, a colossal filament of galaxies spanning an almost unimaginable 10 billion light-years. This is not a poetic metaphor, but a direct causal chain. The microcosm and the macrocosm are woven from the same thread. The fundamental forces that dictate how quarks bind together to form a proton are the very same forces that govern the gravitational dance of 1,000 galaxies in a cluster. There is no separate rulebook for the large and the small. The elegant spin of an electron and the sprawling architecture of a supercluster are both expressions of a single, unified set of physical laws. The cosmic map is not something imposed upon the universe from the outside. It is the emergent, grandest possible expression of its own internal logic. To truly understand the cartographer, we must therefore listen to the entire symphony at once, from the first quantum note to the final, resonant chord of the cosmic web. This profound harmony across 40 orders of magnitude is our most powerful clue that we are on the right path, that a single, beautiful truth underlies all of reality. Information might be the true substance of reality. In our digital world, we are accustomed to the idea that complex things can be broken down into simple bits of data, ones and zeros that can be processed by a computer. A growing number of physicists are now asking if the entire cosmos operates on a similar principle. From this perspective, a star is not just a ball of plasma, and a galaxy is not just a collection of stars. They are incredibly dense, dynamic expressions of information. The particles that make up every atom, the forces that bind them, and the very fabric of space-time could all be emergent properties, secondary phenomena that arise from a deeper, more fundamental layer of information processing. This transforms our entire understanding of the cosmic map. The universe is not merely a place that contains information, like a library holds books. The universe itself is the information. The grand evolution from a smooth, hot fireball to the intricate cosmic web was not just a physical transformation. It was a computational process. It was the universe running a specific, unimaginably complex algorithm, taking its initial conditions as input, and over 13.8 billion years, calculating the output we now see as galaxies and voids. The gravitational collapse of a gas cloud into a star is a computation. The merger of two galaxies is a computation. The entire history of cosmic structure formation is the universe processing information according to the unbreakable rules of physics. This is where the holographic principle finds its most profound meaning. It suggests that all the information needed to describe our three-dimensional reality, every detail of every particle in every galaxy, is perfectly encoded on a two-dimensional surface at its boundary. The cosmos is not a solid object, but a projection, a hologram. The real cartographers, then, are the fundamental laws of information dynamics. The universe is a cosmic computer, and the map we have been tracing is simply the readout from its ongoing calculation. Our quest shifts from asking what the universe is made of to a far more intriguing question. What computation is it performing, and what is the ultimate meaning of its answer? Our cosmic map is a masterpiece of precision, yet its perfection is precisely what makes its flaws so compelling. Astronomers are not just filling in blank spots anymore. They are searching for cracks in the foundation, subtle anomalies where the universe's behavior defies our most cherished models. This is not a sign of failure, but the most exciting phase of discovery. The most prominent of these cracks is known as the Hubble tension. It is a stubborn disagreement over how fast the universe is expanding today. We have two primary ways to measure this expansion rate. One method looks at the ancient universe, using the cosmic microwave background as a starting point and calculating forward. The other method measures the universe directly around us, using stars and supernovas as cosmic yardsticks. Both methods are incredibly sophisticated, yet they give two different, stubbornly irreconcilable answers. It is like having two of the world's most accurate clocks, built by master craftsmen, that insist on ticking at different speeds. This is not a small error. It is a fundamental discrepancy that suggests something in our standard model of cosmology might be missing. Perhaps dark energy is not constant, but evolves over time. Or maybe there is an unknown type of neutrino or another exotic particle, subtly altering the cosmic expansion history. The Hubble tension is a quiet alarm bell ringing through cosmology, urging us to look deeper. But the potential surprises are not confined to the behavior of space itself. They might be written into its very structure. Some astronomers have reported evidence for structures of a scale that seems to defy the cosmological principle. The core idea that the universe should look roughly the same in every direction. What if we live inside a cosmic void, a relative emptiness on a scale of billions of light years, which distorts our local measurements of expansion? Or perhaps we are caught in a vast dark matter current, a cosmic wind pushing our entire galactic neighborhood in a way that skews our perspective. There are other, quieter puzzles. Why do the spins of some galaxies billions of light years apart appear to be synchronized, as if connected by some invisible influence that transcends the speed of light? And what created the mysterious cold spot in the cosmic microwave background? A vast, unusually cold region that some theories suggest could be the imprint of a collision with another universe. These are not mere curiosities. Each one is a potential thread, and pulling on it could unravel our current understanding and reveal a richer, stranger tapestry of physics. Finding a confirmed major anomaly would be the ultimate cartographic breakthrough. It would be like a medieval mapmaker, confident their world map was complete, suddenly receiving confirmed reports of an entirely new continent. The old map, for all its detail, would be instantly rendered obsolete. The search for these cosmic discrepancies is therefore a vital and deliberate process. It is how we ensure our map remains faithful to the territory, no matter how strange that territory turns out to be. These cracks are not flaws in the universe, but windows into a deeper layer of reality waiting to be opened. This journey reveals a cosmos that is its own master cartographer. From the faint quantum whisper of its first instant to the sprawling galactic cities of today, the universe has been meticulously sketching its own portrait across the eons. We have traced the invisible hand of dark matter, the unbreakable rules of fundamental law, and the dynamic conversations of stellar feedback. We have read its history in ancient light and built machines to glimpse its future. The map is not a static relic, but a living, breathing entity, constantly edited by the very forces it describes. There is no external artist, only the magnificent, inevitable unfolding of physics over deep time. This self-cartography is a core property of existence, a process that forges stars, sculpts planets, and carves out the niche for life itself. Our own consciousness is perhaps the most profound expression of this process, a way for the cosmos to not only map itself, but to know its own map. When you gaze into the starry void, you are not a separate observer. You are a part of the atlas, a living page in this grand, self-written story. What other wonders are hidden within the lines of this cosmic chart? Share your thoughts and questions in the comments, and join us as we continue our exploration of the universe's greatest mysteries.